Hello and welcome to a new video. This is for Precalculus using the Math UC curriculum. We're on lesson 18, which is pretty exciting stuff. This lesson is about vectors, and if you've had physics, then vectors is something that you should be familiar with. If you have not had vectors, well, buckle up because you're in for an exciting time. So if you've already had physics, this will be easy. If you haven't had physics and then you go and take physics, hopefully vectors will be easier for you than if you hadn't seen them before. So what is a vector? If you're familiar with a movie called Despicable Me, you already actually know what a vector is, because in that movie, spoiler alert, there is a villain. Not necessarily the villain of the movie, but he is a self-proclaimed villain that he's calling himself Vector because he's committing crimes with both magnitude and direction. Oh yeah. I've watched the movie a few times. So a vector is something that we use in math / science / physics, all that stuff, to talk about something that, yes, we care how much it is, but we also care what direction it is. And vectors actually tend to have something similar that goes with them that we wouldn't include direction on. So for instance, I have a list here of examples of vectors: displacement, velocity, and force. So displacement, you may be familiar with and may be thinking, isn't that just kind of a fancy version of distance? And I would say yes, it's a vector version of distance. So when we measure distance, we're measuring how far we've traveled. But displacement, more specifically, is how far and in what direction we are from our starting point. So if you go someplace and come back to your house, your displacement is actually 0, even though you traveled a certain distance there and back. So that's how we kind of can tie in this idea of direction. So velocity is kind of a fancy word for speed. When you're traveling in a car, right, you have a speed that you're going that your good old speedometer tells you about. But when we talk about velocity in math and in science, we also care about, is it a forward velocity? Is it a backward velocity, or left or right? Because then you might see negative velocities to show that you're going backwards, or a negative velocity might show that you're going left instead of right. And force, which is definitely one of the things that you encounter in physics when you're pushing on something, or when gravity's pushing on you, or friction is, acting on you. All of those things have a direction because, there's this idea of forces interacting with each other make something move the way it does. So that's kind of why we use vectors. We actually represent vectors, we can represent them at least, in a coordinate plane sort of situation. We don't normally represent it, we don't normally use polar coordinate planes, even though the reason this is coming up when it is because this is very, very applicable to using polar coordinates. Polar coordinates give us a magnitude and a direction. That's exactly what we need to have a vector. But if we're trying to actually think of the interactions of two different vectors, it's more helpful actually in some ways to know the x component and the y component of that vector. So in this picture I have on the screen for you, we have two vectors that are blue, and then we have a vector that connects them from the start to, the end, that's green. What this is actually showing is, let's say that the two blue vectors are us moving somewhere. So we first move along the first blue vector from 0, 0 to 4, 6, and then we move again from 4, 6 to 12, 4. Well, at the end of that, we will have moved from 0, 0 to 12, 4. That would be like our displacement, right? So in order for us to kind of figure this out, we actually need to think about the x and the y. And it's really obvious whenever you have kind of an easy situation like this, that all of these were nice points. It's really easy to be like, okay, so, we've got a 4, 6, and we've got and then it moves over, 8 more, and it moves down 2. So where do we end up? At all of those things I just mentioned were x and y coordinates. And so it's actually really, really helpful both to be able to think of a vector as its magnitude and direction, because that is an important way of thinking of it, but also to be able to break it down into what is actually happening to us each of our two main directions, x and y. because then we can see how vectors interact with each other by adding them together. When we do that, when we add two vectors together, we get what's called a resultant vector, which just think of the word result, right? That's an answer. So that gives us our resultant vector. So we can represent vectors as polar coordinates. We can also use x and y components. There is a really cool way, in my personal opinion, that we use to signify vectors, which is we assume that it starts at 0, 0, and then the end point of your vector, you put in these like fancy arrow brackets. It's the only place that I know of that arrow brackets are used is for vectors. And so having arrow brackets around 12, 4 refers to this green vector that we have drawn here that has an end point of 12, 4. There are two other ways-ish, there may be more, that we can do it. A pretty common way to represent vectors is to have, again, the x and y components, but then have letters next to them. The most common being I and j, which I'm not really sure who decided to pick I and j. I would not in this case be talking about an imaginary number. It's talking about going 12 for x and 4 for y, even though we're using I and j instead of x and y. Or I believe the Math UC book actually defaults to using something like 12x plus 4y, which does actually make sense, but I don't know that I've ever seen anyone use x and y there before. Go figure. So all this is to say, we're going to be adding vectors together, and that's going to require us using what we know about polar coordinates is really the easiest way to think of it, since that's what we've done the most recently, that we need to be able to take something that's a magnitude and direction and change it into its x's and y's. To do that, I'll go ahead and make a note here. To do that, we need basically that cool set of formulas that x equals r cosine theta and y equals r sine theta that we use to convert between. And then we also will need to be able to convert back, because if they give us the problem in polar coordinates, typically they will either ask or just we should know that they want them back in a polar coordinate at the end. So we will also use the Pythagorean theorem to be able to get back to the magnitude once we have our new vector, and we'll also end up using inverse tangent of y over x to get the new angle that we would use. So let's go ahead and take a look at example 1. Example 1, find the polar coordinates of the addition of the two vectors. So in the Math UC book, especially if you read the teacher handbook part of it, the teacher, the author, whoever you want to call it, whatever you want to call them, spends time talking about vectors as throws. So we could imagine it that way, that like you're starting at 0, 0, you're doing one throw at a certain magnitude and direction, and then you walk to where your object landed, you pick it up, and you throw from that location. And so then essentially it's asking us for the resultant vector from 0, 0 to where we ended up after the second throw, or that ball or whatever you threw ended up. So what we're going to do here is change these both to x's and y's, the x and y coordinates, and then add them together and then change to polar coordinates. And you could find it helpful to actually draw this. I don't know how helpful, but like we could draw it and kind of get an idea of what we think it would look like. When we draw vectors, this is going to be mediocre at best. When we draw vectors, okay, we're going 87 degrees and then 3 feet. So that's almost 90. And compared to our 11 feet, that's not very far. There's two ways we draw vectors when we're adding them together. One way is like what I had on the previous slide, where you have at the end of the first vector, you draw the second vector. So when we do that, we don't want to think of this 24 degrees as though we're trying to turn 24 degrees. It's actually like we have a new coordinate plane here, and we're saying, okay, what is 24 degrees from standard position? Okay, so that would be, not even 30. So something like this. And this one's longer. Now this isn't gonna end up being perfect by any means, but the more you take into account, like, which one's supposed to be longer and about where do you think the angle should be, the closer your figure will actually look. There's actually a lot of ways that we could go ahead and find these things, like this is a triangle, an oblique triangle. So I can't help but think that we might have enough information to actually try to use law of sines or law of cosines, but we don't normally do that. Normally we just convert to x and y, add them together, and then convert back if needed. So remember that to convert, we need to do 3 cosine theta. So 3 cosine 87. Make sure you're in degree mode. I'm grabbing Desmos on my other monitor. So I need to change to degree mode. If you're on your TI calculator, remember that it says up at the top radian or degree. The reason that the way to tell that you are going to need to be in degree mode is the degree symbol on 87. So that sounds kind of sarcastic maybe, but that really is how we tell whether we want to be in degree mode or not, is that if there's a degree symbol, you should be in degree mode, and if there's not, then you should not. If you don't have an angle listed at all, then it does make it a little trickier, but I'm going to do like 3 decimal places here, just cause. So that's the x value and the y value. So because it's so close to 90, that's why I'm getting kind of what might seem kind of like some weird answers here. Like this was almost 3 and this is almost kind of close-ish to 0, because that first vector is almost a vertical vector. Vertical vector, vertical vector. All right, let's do the second one here. So 11 cosine 24. And then 11 sine 24. So that is 10.049 and 4.474. So we're adding these together to get our new and improved resultant vector. And I personally don't want to have to add these together in my head, so I'm actually doing a little copy paste action here to have Desmos do it for me. So this first one is 10.206. And the second one is 7.469, which would round up to 7.470. All right, so this is if we wanted just x and y components, but it does actually specify to find the polar coordinates. I thought for a second, I was like, does it? Yes, it does. Find the polar coordinates. So essentially what we've got right now is that this side of a right triangle would be 10.206 and this side would be 7.470. And so we're using the Pythagorean theorem to find the magnitude and inverse tangent to find the angle. So we got this squared plus this squared, and we're going to square root it. That's going to be our magnitude. That sure is. So at this point, I would kind of like to round actually to just like 1 decimal place. In some ways, it doesn't really matter, but this is 159. Actually, if I round to 1 decimal place, this rounds up to 160. Oh, but I haven't square rooted yet. Hang on, let me square root. That's an easy thing to forget, apparently. 12.6, okay. So this is 12.6 and we are in feet. That's what the apostrophe at the beginning meant. And then our angle comes from doing inverse tangent of the y value, because that's the opposite side, over the x value. And if you're like, I'm not getting exactly the same thing as you, why is that? That would be because I am actually copying and pasting so that I'm not rounding in actuality the same way that I've been writing it down. So my apologies, because that might be a bit confusing. Okay, so this angle should be 36.6-ish. And so we would write this as a polar coordinate point 12.6 feet, comma 36.6 degrees. And when we write it in polar coordinates, we would not use the arrow brackets. It's only whenever we're writing it with x and y components that we would. Okay, so example 2 here is really similar. Like basically it's the exact same thing. The only thing different is that I put some negatives in here strategically to make this maybe make this be a little more interesting. I don't know if it actually is, but I thought we could give it a try. So if we are drawing a coordinate plane here to kind of get an idea, keep in mind that 50 degrees is in the first quadrant, but then you'd actually go across the origin the other direction to do -6. So I only needed the first quadrant in example 1, but here I think we would need to actually have multiple quadrants. I also want to show you there's a different way that we can draw these vectors. We don't have to do it where the second one is starts at the end of the first one. There's another way we can do it. So if I say that 50 degrees is about here, then -6 is going to be this direction. So I could say it's something like this. And then -40 means instead of going +40, I'd go into the fourth quadrant. And I'm gonna, well, okay, that needs to be longer because 8 is longer than 6. Let me try again. So something like that, I don't know. So there's a way that you can do this where you basically make a kind of parallelogram happen. That you kind of, now that we've got that, we kind of imagine where these would meet out here, and that's actually what our resultant vector should look like. Now, I have not been, this was not done super accurately, so keep that in mind, that I am not confident enough in how I've drawn this to like guess at what the answer is, even though I've already done this problem one other time before. So it is going to be a good idea for us to find the x and y coordinates. So -6, and put the negative in so that it gives us the sign we want, because -6 cosine 50 should give us a negative because it should be in the third quadrant. So it gives us -3.857. And then we do the same thing but for sine, and it should be -4.596. Okay, that's our first one. Then we're going to do 8 cosine. So then we're going to add these together and then convert them back to polar coordinates. And again, the signs are important here. So this first one ends up being 2.272, which actually I feel like I did a decent job on my drawing, a much better job than I did whenever I did this in class actually. Now let's convert this to polar coordinates. Now, when we're doing the Pythagorean theorem and we're squaring this negative number, you either need to put it inside parentheses with your squared on the outside, or you need to just not put the negative at all. Because if you leave out these parentheses, the negative doesn't get squared, and it's supposed to get squared. So that would be an easy place to mess this up. And if you do mess that up in that way, you're going to end up with your calculator saying it can't do that because it's going to give you an imaginary number. So when we square root this and everything, this ends up being 10 almost exactly. So that's kind of fun. And we're going to do inverse tangent. Now, if our answer was in the second or third quadrant and we do inverse tangent, we would actually have to do more work to find the correct angle, because inverse tangent can tell us this positive angle or this negative angle. But when we use it to try to find an angle here or here, we actually have to add or subtract from 180 to get the correct angle. It's not going to happen to us here, but it could happen to us later, so I thought I'd throw it out there. So inverse tangent. -76 point, I'm going to round to 1 decimal place, so negative 76.9 degrees. So this would be 10 feet, comma, negative 76.9 degrees. What I like about drawing the picture is that it kind of reinforces that, okay, we probably did things right, because you know what, that does look like, it looks like it makes sense, right? Whereas if we had ended up with an answer like 50, a positive 50, it'd be like, wait, either I really drew this badly or somewhere my math went wrong. Example 3, this is a little different, not just because it looks different, but it gives us different information and asks us for something different. This time it gives us the first vector and the resultant vector and wants us to say the coordinates for the second vector. And if when I first tried to do this the other day, it threw me off because I was like, wait, how am I going to draw this? But I think I've got it figured out now. The first throw is at 330, which is over here in the fourth quadrant, and is a length of 6. The resultant that they're giving us is at 33.413. So that's going to be longer by quite a bit, like almost twice as long. So what we're trying to find the second vector, which would be this vector right here. This is what we want to know the magnitude and direction of. So it's going to be a really similar process. Just kind of think about what's different. If instead of taking two vectors, adding them together and getting the result, we know one of the vectors and the result, we're going to subtract instead of add, and that will give us the coordinates for the second vector. So let's find our first vector, which we do 6 cosine 330, and gives us 5.196, and then we'll do 6 sine 330 and get -3. Because that is actually a reference angle of 30, we probably could have done this differently. Like with special right triangles, I mean. So our resultant vector, 13.4 cosine 33.4, that's 11.187, and the y value is 7.376. That was good. Okay, so we want to subtract these. Now keep in mind that when we subtract here, we're going to do this 11 minus this 5. But then when we do the next one, this 7, if we minus -3, we either need to put in to our calculator minus -3, or we need to say, oh, that's really addition. I'm really going to do 7 plus 3. And it doesn't matter to me which way you do it, just so long as you do it right. Oh, I'm almost screwing this up. I want to do the 11 point blah 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 minus the 5 point blah blah blah. That gives me 5.991, and then I'm gonna do the 7.376 minus a negative, so I'm gonna do, wait. Yes, okay, plus 3. 10.376. And then we're going to change this to polar coordinates. I mean, I don't know that it says to, but like we should. We might as well, that kind of thing. So if we round this to 1 decimal place, we get 12. And then we're going to inverse tangent. And it looks like this is a, like if you imagine that the origin is here, right? This looks like an angle in the first quadrant. So we shouldn't have any issues using inverse tangent. And I get 60 degrees. So this time we don't have units. I think I just forgot to put units. So we get 12 unknown units, comma, 60 degrees. So that was how we would do that if we're missing the second vector instead of trying to find the resultant vector. Thanks so much for watching. I hope that you enjoyed this video. If you did, give me a thumbs up. Please subscribe if you haven't already, and I'll see you in the next video. Thanks.